Okay, now we're into section 1.3. Here we want to look at the conjugate of Z. Now, to start, though, let's point out, if we talk about Z equals X plus IY, then the real part of Z is X, and we usually write something like RE of Z, and then you would say equals X. And then the imaginary part of Z is Y. Now, this, is something very important to realize, is that the imaginary part, so Im of Z equals Y, is a real number. So if you have something like Z equals 3 plus 2I, then the real part of Z is 3, and the imaginary part of Z is 2. Okay, not 2I, but 2. It's the real number 2. And, so similarly, if I had something like minus I, then the real part of Z is equal to 0. And the imaginary part of Z is equal to -1. Okay, so that's real and imaginary parts. Now we get to Z conjugate. Okay, the conjugate of Z. In that, we use the symbol Z bar. And the conjugate, so if we have Z equals X plus IY, then Z conjugate is X minus IY. Now, similarly, though, if Z were to equal X minus IY, which is not standard notation, but, if you were looking at something like that, then Z bar would be X plus IY. And so from that we get some very nice properties. Let's see, so this is all from proposition 1.5, and so A, they just have that Z1 plus or minus Z2 conjugate. So if you've got a conjugate over an addition or subtraction, that distributes over that addition or subtraction, and so you can take the conjugate in any order, is what that's saying. And similarly, with multiplication, if I got Z1 times Z2 and I want the conjugate of that, I can simply do the conjugate of Z1 times the conjugate of Z2, so that's nice. And similarly with division. So if I have Z1 over Z2, then in conjugate, then that's the same thing as Z1 conjugate over Z2 conjugate. D. Let's see, I need to look at D here. Oh, yeah, so that's just, if you want the conjugate of the conjugate, you just get back Z. But again, you know, looking up here, right, we already kind of pointed that out with those two items. E, the absolute value of Z conjugate is equal to the absolute value of Z, so the modulus of Z conjugate is going to be the same as the modulus of Z. But of course, again, that makes sense in that we haven't changed X or Y, really. I mean, we've just gone with the negative on Y, and so we haven't changed their size. So when we do that modulus, we'll get the same answer. F, now this is very nice here, is that if you want the absolute value of Z squared, then you can take Z times Z conjugate. Now, and from E up there, notice that, well, that would also be the same for the absolute value of Z conjugate squared. So that is a very nice characterization of the modulus of Z. Well, modulus of Z squared anyway. G, the real part of Z. We can find that simply by taking Z plus Z conjugate and dividing by 2. And the imaginary part of Z, we can get that by taking Z plus, not Z plus, Z minus. Z minus Z conjugate, and then over 2I. So we will need the I in there because we got to get rid of the I. And then finally, the last property I is that if you've got E, so if you've got the polar notation and you want the conjugate of e to the I theta, that's just e to the minus I theta. So if you're using your polar notation, then you can get a conjugate simply by taking the negative theta. Now, on I, here's a nice picture of that, is, right, if I've got Z out here, and that was, you know, an X plus IY, so that's Y there. I, and then the conjugate is X minus IY, right? So I would just come down here. So X is the same. So here's Z bar. There's minus Y. But notice then, if that's theta, that's minus theta. So that's a you know, nice graphic as to why I works the way it does for the conjugate. Okay, so that's another geometric property visually, is that we are just using symmetry over the x-axis or the real axis. Okay, so those are a bunch of the properties. Now, you know, the textbook does a proof of B. And that's that Z1, Z2 conjugate is Z1 conjugate, Z2 conjugate. And, you know, in some ways you could do these in in any sort of order. So their proof in the book they prove this by using, z1 equals x1 plus I y1, and z2 equals x2 plus I y2, and they go through the algebra of just multiplying all that out and regrouping and and pointing out that this is true. Now, but notice if you've already proved I, say, so if I had that, then I could say z1 equals r1 e to the I theta 1, and z2 equals r2 e to the I theta 2. And so if I take z1, z2 conjugate, that's r1 e to the I theta 1, r2 e to the I theta 2 conjugate, which is r1, r2 e to the I theta 1 plus theta 2 conjugate. Well, there is no conjugate to the r's because those are just real numbers. So it's all about the I theta up there. And so then this is r1, r2 e to the negative I theta 1 plus theta 2, which is r1, r2 e to the negative I theta 1 minus, plus, we'll say, negative I theta 2. And so then that's r1 e to the negative I theta 1, r2 e to the negative I theta 2. And so there we have our z1 conjugate and then z2 conjugate. So you see, you can, if you already had the proof of I, if you knew that was true, then you could have used that notation to prove B, or the Z1, Z2 conjugate. Okay, well, let's see. So, then I guess, well, let me toss in one. They then mention another property right after this before they get to the triangle inequality. So let's point this one out. They say, okay, z to the negative 1, which is 1 over z, is equal to z bar over the magnitude of z squared. Okay, now that's not amazing. That's quite easy to show in that notice that z bar over z, the absolute value of z squared is just z bar, and from, again, a previous property up above, you have z bar. And of course, well, z bar over z bar cancels and you get the 1 over z. So, this is not an amazingly deep thing. It's just taking 1 over z and multiplying top and bottom by z bar. Okay, so we'll call that good for this video.